Future, as I said, we're delighted to have Lawrence O'Rourke, who was originally from Mullingar, though he's now based in Spain, working for the European Space Agency. He's given several talks in the past about the Rosetta spacecraft that went to Comet 67P, to give it its short name, and dropped that Philae lander onto the surface of the comet. Unfortunately, it bounced a bit and went missing for, was it 2 years? 2 years or so, and Lawrence actually led the team that found it just before the mission came to an end, in fact, just the last minute. A nice dramatic story. He's spoken about that in the past. He started off working in the 1990s for ESA. He's been not just in Spain but in Germany as well. He worked on the Herschel infrared space telescope and lots of other missions as well. His CV is too long to mention. You can read a good bit more about it on our website. But after the Rosetta mission ended, he moved to the next big mission that the European Space Agency is running, called Plato. That's what he's going to tell us about this evening. He's done incredible work in the past, including finding some of the first water on an asteroid, which may sound a bit esoteric, but in fact it's probably what most of you are made of. The Earth shouldn't have this much water, having been produced from a very hot planet as all the bits impacted each other and raised the surface temperature of the Earth to a point where it couldn't support water. Where did all the oceans come from? We think asteroids or comets bombarded the Earth, filled the oceans, and you and I are carrying that water around inside every cell in our body. Probably 2/3 of us is made of either comet or asteroid juice. So he was the first person to find this actual water on an asteroid. So he has a fantastic repertoire of discoveries. In fact, so much so that the International Astronomical Union have named an asteroid after him. So there is no O'Rourke in space. But tonight I'd like you to welcome the O'Rourke in Trinity College. Please give a warm welcome, Lawrence O'Rourke of the European Space Agency.
Like this?
Thank you like that?
Can Seamus hear me? Put it in my pocket. Okay. Thank you very much, David. He's just gone out for a second, but it's very much appreciated introduction. Get some water before I start. Indeed, I very much appreciate the invitation from Astronomy Ireland to give this talk to you. I also very much appreciate you all taking the time to come to listen to me on this very stormy evening. I think it's I was afraid I'd be looking at empty rows, and it's really very I'm very happy to see so many here. So I'm going to talk tonight, and I want to dim the lights because otherwise you won't see anything of the presentation. And let me see how I do that. Is that okay? Too dim, or it's okay? Okay. Anyway, if you you know where the emergency exits are, so it's well enough to see. I'm going to talk today about things which you well, it's a theme which appears in a lot of the newspapers. It's practically every week you hear about new planets being discovered, Earth-like planets, and I just wanted to give my own viewpoint about what the media is telling you versus the reality of actually what is being found. And also talk a bit about my own mission, the Plato Mission, which is there to try to find Earth's twin. And then when we found it, well, I also touched upon the theme of how on earth are we going to get there, because it's not just a case of finding it, you actually want to travel. And I want to talk about the rockets that are being built at the moment, how fast they go, and the techniques we use to try to speed up in space, and the challenges that we're going to have to try to get to this future Earth. So let me jump straight into the European Space Agency. I've been working for the European Space Agency over 20 years now. We touch on many different things. We have our astronauts, we build lots of satellites, we have our rockets, which I'll talk about later on. We have control centres around Europe, and one of them is in fact in Spain, which is where I'm working, just outside Madrid. It's the European Space Astronomy Centre with about 25 different missions being controlled from there, including Solar Orbiter, the satellite which was launched only about 12 hours ago from Cape Canaveral. And we take care of the science operations, or let's say everything that's got to do with the instruments on board these satellites, how you point a spacecraft, where you point it in order to get the maximum science from these instruments. That's what we do there. And so we have in this location, we had the Rosetta Control Center, which is what I was leading, and now we're looking after the Plato Mission, which I'll talk about later. So to talk about exoplanets and what we're seeing, you have to really go back to our own solar system and its formation, and then ask yourself, well, are we alone in the universe? And is what we're seeing in our formation, is it similar to what's actually been seen in other places? And this is this is the formation about 4.5 billion years ago of our solar system, which was formed from the gravitational collapse of a cloud of gas and dust, which, revolving over time, effectively with continuing pressure in the center, resulted in the sun being formed. And the sun then burns everything that's close by to it and gradually pushes the dust out, and the dust itself starts accumulating and the gas starts accumulating, and what you end up in the end are the planets which we have. The planets of the more rocky planets closer to the sun, and then you have the Jupiter, the gaseous planets which move further away. So what you have pretty much, and I'm trying to see now if I can see what, because I can't see my own, okay, I keep my finger on the arrow. So what you're having here is our solar system then has got, if you look at it from a distance, you see all the planets, you see we have between Mars and Jupiter we have an asteroid belt, and then as you go further out, beyond Jupiter, beyond Neptune, you end up with the Kuiper belt, the Kuiper-Edgeworth belt, and Edgeworth, in fact, was from Westmead, in fact, and helped discover this belt of comets, which is beyond Neptune, and even further out, even out to a distance about let's say 15 trillion kilometers, you have what's called the Oort cloud. So this is a huge, from a distance, if you were to look from another star, you would very much see a disk sort of structure where you see the comets you see this cometary sort of structure all around on the inside you see the planets. And the question to be asked is, well, the formation process that occurred okay, thanks. Okay, thanks. So the formation process that we see in our solar system, do you see it out there around other stars? And the answer is yes, because this is what we're seeing. When you look at the sky in the far infrared, you actually can see the dust. And you look at certain stars and you suddenly start seeing that stars also have their own protoplanetary disks. You see this dust cloud where, and the more you focus in, you actually see that they can have planets on the inside. So it's not alone in that respect. But how do we know? So now we know there might be planets around our stars. Well, how do we find them? So what I want to talk about is a bit about the techniques that we use to find this. We see there's these clouds out there that look like our formation, the formation of our solar system. Well, how do we find them? And so the steps involved to find Earth's twin would be, you effectively have to follow 3 different steps. You've got to know your star, you've got to know the planet, and you've got to determine can we live there. So know the star. Well, you need to understand what's the star type, what's the star size, mass. When you know the star itself, how old it is, then you actually can understand how old the planets are around it. And looking at the planets, you try to find the planets around them. You find out how fast to go around. You can find out the distance, the orbital period, and you actually can even determine the mass and the radius of the planet, exoplanets as they're called. And when you find this, then you want to study in detail. If you can find them in what's called the Goldilocks Zone, I'll explain that in a minute. And you also want to see if you can see the atmosphere. Can you see water in the atmosphere? And in the end, we're trying to find water, because that's really the makeup of our body is so much of water, but also the seas and everything that it makes up this planet, and the beautiful rain that's, well, okay, let's rephrase. The rain which is outside is all based upon things that we need for life. And so let's look at the first one. Let's know our star. What's the star type? What's the star size and age and mass? And let's look at our sun. Now our sun is it's called a G star, a G-type main sequence star. Okay, that's quite scientific, but effectively it's a dwarf star. So we were all hearing about red dwarfs and white dwarfs. Well, our star, in fact, is known as a yellow dwarf. It's yellow, it looks yellow, but in fact, if you go to space and you go outside our atmosphere, our sun actually is not yellow, it's white. Because the atmosphere we have is actually absorbing different colours, and you actually get a yellow sort of tinge when we look at it. But the reality of our sun is it lasts a certain number of billion years, and the future of our planet and the future of our sun is pretty much that we've got to go through certain events before our sun explodes, and I'm going through them, just the more local ones, whether we get a hung Doyle and we got more general elections coming up. I expect by the time we actually have a red giant, we actually Westmeath will win the Sam Maguire. That's what I certainly expect that sometime. But at the very end of this, okay, the very end process is that our sun will gradually get bigger. It will change from being this white star to get bigger and bigger and bigger, slowly enveloping all the planets which make up our solar system. It becomes a red giant, and effectively that's the end of our Earth as we know it. We will want to have found another planet like ours in order to be able to travel there and escape from this one, because it will no longer exist. But okay, I don't want to alarm you, we're talking billions of years, so we have time. But, okay, let's try to see if we can actually find this Earth. Maybe we're going to find it in the next 10, 20 years. Can we see it? Can we find it? So, knowing what our own star is like, let me talk a bit about how the media is presenting, where we talk about Earth-like stars and Earth-like planets and the stars have been found on. A lot of the stars which exist in our universe are primarily red dwarfs, and in fact 2/3 of the stars which are closer to our sun are red dwarfs. Now these are a few tenths in size of our sun. The effective temperature of is much cooler, so they last much longer. It can last up to 100 billion years. They're cooler than our sun. Our sun is about 5,000 Kelvin. And the reality is that because they're cooler, then you can actually have planets much closer, and you can also have the temperature of boiling of water you can have the let's say water in liquid form much closer because it's a cooler star. But the question is, can you actually live close to one? And I want to talk about that later on. Okay, so now we knowing a bit about the stars that are in our universe, mostly red dwarfs. So we want to find some planets around these stars. And you want to understand to understand the planet, you must understand the star. And so the first thing you want to know is you want to look at star radius, the mass and the age. And you can determine this because all stars, including our sun, oscillate. They actually expand and contract. And depending on the age of the sun, of the star that you're looking at, it will actually expand and contract differently. And so just by this, you can actually tell from the resonance frequency, you can actually tell its mass, its angular momentum, and its age. So if you know, just like how we do, that our sun is about 4.3 billion years old, then at least you know if you find planets around it that they're younger than 4.3 billion years old. And this gives you information about knowing the age. Then you can actually move on to look about the planet. Now the planets themselves, I mean, we want to look at the planetary orbit, the year period, and the question is, how do we find planets around stars and a night sky? You're looking at how actually is it feasible to find planets. And there's different techniques out there, and I'm going to talk about the 5 that we use. There's ones which are less successful and the ones which are more successful. Now there's about 4,000 planets, exoplanets, have been discovered around stars, other stars than our sun. 4,000. And how do you find them? Well, there's different techniques. The one on the left, astrometry. There's only one planet discovered with astrometry. And astrometry is very difficult because what you're looking at is motion. You're looking at stellar motion. It's where you look at this star and you need to have a very precise measurement of its motion, how it moves through the sky. And with this technique, they've actually discovered one star where you actually see that the motion is affected by something which is going around it. And this was how they discovered a planet around it. But this is a very, very difficult technique to use. Another one is direct imaging. Okay, so you look at a star and you just look with a very, very high caliber, high quality telescope, and you can actually see if you block out, which is a technique to use in astronomy, you can actually block out the star, which is blinding everything around us, and you can actually make out the planets which are surrounding, this is the direct imaging technique. And with this, you've discovered 44 planets. And then you have microlensing. Now, microlensing is quite cool in ways, in that they use objects which are in the way, in your field of view, effectively like a lens, and it actually gives you it effectively can give you a bigger view of what's behind it. And so with galaxies, they can use it, and you can find the planets also which are effectively magnified by something which is in your field of view. And so they've discovered 64. But these are just the techniques which are less successful, and then we've got the ones which are a bit more successful. And this one is the key technique, which is the transit technique. And it's let's go to here. This is where it's very much a case of that each star is giving out light, and when a planet, which is going around the planet, which is around the sun, goes in front, that light diminishes, just for a short period of time. Can be minutes, can be hours. But because of this, when you're looking at it, you look at multiple stars, many thousands of stars, you actually can see how the light can change. And from this, you can actually determine that there's planets there. Knowing there is a planet there, you also want to, so now we found, okay, with these 4 different techniques, now you found that there's planets around the stars. And primarily we use this transit technique. You see the light dimming, this tells you there's a planet around it. Now you want to understand, okay, how big is this planet? How heavy is it? What's its radius? And to do this, you use the technique of radial velocity. And this is something which you do from ground. So you can use ground-based observatories. And radial velocity is a very, cool technique, I think, in that the light which is coming, which is consider like a rainbow. The light is a rainbow of colors. Effectively, the sun itself, the star itself, is being pulled by the planets which are surrounding it. So just like our sun has planets going around, and we're actually pulling from a gravitational perspective on our own sun, so these planets also are pulled. And depending on the pull, and depending on where the star is, the planet is with respect to this star, you can actually measure how its mass, how much it's pulling, and therefore determine its radius. And so, in summary, basically from the photometry, from the fact that you actually now know how old the star is, what its radius and its mass, you can actually see that there's planets around, that you've detected it. So now you have the planet age and you get planet radius. You feed in the planet mass because you've just seen it pulling on the star a certain amount with spectroscopy. And then from this you have, in fact, you understand now what you characterize, let's say, you understand a lot more what is the planet like. But you're not finished there, because you still don't understand whether it has what is the atmosphere it has, is it livable? And this is where we move on to the third point, which is, can you live there? And we move on to the idea of what's called the Goldilocks Zone, which is in fact the key to life on Earth. Now, it's called the Goldilocks because it's based on the idea of something being where Goldilocks goes to the house and she has the porridge. It's not too hot, not too cold. Well, one which is too hot, one which is too cold, and then there's one which is just right. And similarly the same with the bed, etc. And this is the idea of the location of where the Earth is around the sun. It's not too hot. It's not close to Venus or to Mercury, where the water on our surface will just boil off. Or it's not too cold. You go out towards Mars, where everything will be ice. Effectively, it's in this what's called the habitable zone. And depending on the temperature of the sun, of the star that is going around, the habitable zone, this Goldilocks zone, can be closer or can be further away. So for the very hot stars, hotter than our own sun, hotter than 5,000 degrees Kelvin, then this zone has to be much further away, because otherwise all the gas, all the water will be gone. For sun-like stars, okay, we know where it is. It's exactly where our planet is, where the Earth is. And for cooler stars like red dwarfs, now the planet can be much closer. And this is a key technique in understanding what is a habitable zone, a habitable planet. It's an Earth-like planet in that you can actually live there in principle. We'll discuss that in a minute, what that means. But now you have, from the orbit, from the time it passes in front of the star, and it repeats in its maybe 30 days later, it repeats in its, it passes. You see the transit, you see the light going down, so basically you know that the orbit is every 30 days or so. This tells you how close it is, and this at least gives you an idea whether it's in this habitable zone because you know the temperature of the star. But then you want to look at the atmosphere. And it's all based on looking at the atmosphere is using spectroscopy. So it's really looking at the spectrum of the light which is coming. And as the planet is passing in front, or even on the sides of the star, the atmosphere of the planet, as the sun's light passes through the atmosphere, the planet's atmosphere absorbs some of that light. And so the light you actually get when you look at a star will be different because it's absorbed because of the atmosphere. And this absorption lines, these lines where you actually get less light of a certain frequency than you would expect if there was nothing in front of it, tells you what the gases that are in the atmosphere. Therefore, whether it has an atmosphere, therefore what gases you have, it has, and therefore whether it has water, for example. And so okay, you can use this with Hubble, for example, which is being used, but we also have with the European Space Agency, we have another mission which is planned to launch in 2028, which is called Radial, and that's dedicated purely in looking at stars and looking for atmospheres. But it also can be, you can look for atmosphere from the Earth. So from all of this, basically in summary, you've got your characterized, because now you know your planet, you know where it's located, and you've actually also got spectroscopy. You actually understand what sort of atmosphere it has. And with all of this information, the question has to be asked, well, surely, based on this, with the 4,000, or more than 4,000 planets which have been discovered up to now, well, surely our Earth's twin has been discovered. And the answer is no. And it's got to do with the type of stars that's been looked at. And here in this graph, you have the Earth, which is you see one. Basically, follow the two lines of the one on the bottom, the one on the on the left, and the one on the bottom, the X and Y axis, and you see the Earth's there. And there's not very much around it because you're trying to find a star, which you're trying to find the right star, just like our sun, and you're trying to find an Earth-like planet like ours. And with the 4,000 stars, I can confirm that none has been discovered just like our Earth. But we have lots of other types of planets being discovered because you have hot Jupiters. Jupiters, planets the size of Jupiter, which are just closer to the star, and just the atmosphere being burnt off. You have lava worlds, which are much smaller, but again, you've got like Mercuries, but they're just gradually burning up as well. But you have also things called super Earths, and these are the ones which are mentioned a lot in the media. Because, okay, they're not the same as our Earth, they're just much bigger, but closer to Neptune size, but still they're like the Earth because they're just called super Earths. And then you even have special ones like the ones from what you even see in Star Wars, where you get to see two suns and you actually have planets orbiting multiple stars. And so with all of this, this is what you're finding. We're finding planets, lots of different types of planets, but none like our Earth. And the reason is pretty much like this. It's got to do with the techniques you use to try to find them, what type of satellites you're using and how long you're looking. This here is called the Trappist System. It's in the middle between our solar system is at the bottom, the Trappist System, and then just to give you an idea of size, you've got Jupiter and its moons at the top. The Trappist System are a group of about 9 planets that have been discovered by the Trappist Consortium. It was presented in major media release a few years ago, saying, look at all these planets, isn't it fantastic? Surely there's an Earth-like planet among them, Earth-like. But when you look at where it's located in this viewing point, look at how the dotted lines. Yeah, we've got a pointer, excellent. Great, thanks. Good, thanks. Much better. So when you look at basically follow the line, you can see that this whole system here is located inside the orbit of Mercury for our sun. And yet, okay, this is, therefore, what's strange? What is it about this star that allows all these planets to be actually so close to it without burning up? Because it's a strange location. And then there's another one which is even just during the summer last year, which was called K218b, which was a planet which was discovered with a huge amount of water, which is fantastic. Really, they were saying, oh, this is a place to go. But they couldn't really tell you much about how much water in the atmosphere. They were thinking it could be raining all the time, which I don't know is the place we'd actually all like to go to if it's raining all the time, or whether it has only a few drops on the surface. But again, the point to be asked is, well, what's the star type? If this is such a great planet to go to, it's got so much water, what is it that, why is it we can't call it our Earth's twin? And the reality is that because they're red dwarfs. They're different. Our one is the yellow dwarf, they're red dwarfs. And I want to talk a bit about red dwarfs, because this is where now the key comes down to what is the difference between an Earth-like planet versus an Earth2, okay, the Earth's twin. It comes down to the star, which is, I call it, let's say, the good and not so good things about observing planets around, or actually even living on planets around there. Well, I mean, with a red dwarf, because it's a cooler star, well then the Goldilocks Zone is much closer, so it's effectively you can have Earth lie on a planet with water in it much closer, but closer means that the year is shorter, so therefore the orbit is much faster. And you can have an orbit which actually lasted 33 days, for example, so it's a very fast moving orbit. That's a good thing, let's say, about it. You can actually, just with a short amount of time, you can actually you can see this planet pass in front of the star with this transit mode. You see the light dimming. Every 33 days you see it, and it's a great way of tracking and seeing the star, this planet. But what's the not so good thing? The not so good thing about red dwarfs is the following. Okay, it's the radiation poisoning. Okay, they never mention this. Okay, it's full of water, but the problem is that red dwarfs themselves are releasing a huge amount of ultraviolet radiation, a huge amount of X-rays, and so it's not just a case of the fact that it's raining. It's more the fact that you would probably need a huge amount of sun cream, like this gentleman here should have had, and the reality here is, with the radiation poisoning which you get, which means you cannot live there at all, from our perspective, for our species, from mankind cannot live there, then what is it that's living there? And the reality there is, well, if there is life on these Earth-like planets, well, it's certainly not like what we have on our planet. So basically, my best one here is it's like Jim, but not as we know it, effectively, because it's whoever's living here is just not. It doesn't look at all. It's just cannot live on the surface of these planets. So basically, to find Earth2, well, something which is like our own, we need to look at stars like our sun. Okay, so not red dwarfs, which are producing this huge amount of ultraviolet radiation. You need to look at stars like our sun and have a lot of patience. And patience is a virtue. But the question is, why do you need to have patience in order to try to find stars, planets around the stars like our sun? And the answer is because if you look at a star like our sun, we orbit the sun in 1 year. So you need to be looking at a star for at least 2 years to confirm you actually see it passing in front of this star. So to find the Earth, you need to be looking at the star for 2 years. To see it pass over once, and then 1 year later you see it pass over again. And that's how you find the Earth. And there's not many telescopes or satellites out there which actually have the patience. In fact, the majority of the satellites which are out there, whether it's Kepler or whether it's TESS, etc., they're all looking for looking at red dwarfs because it's handy. The zone where you actually see these Earth-like planets are much closer. You see an orbit passing every 30 days, but it's not the same. You effectively need something like this mission here called Plato. This one, which is my next mission, to actually find a planet like the Earth. So the Plato mission, it's named Plato, planetary transits and oscillations of the stars. So effectively you're looking at the oscillation of stars, and then, okay, when you know how old the stars are, then you look at the transits that are passing in front. Well, it's a 2-ton spacecraft. It's launching in 2026 on an Ariane 6 rocket. It consists of 26 cameras. Okay, 26 cameras which are all going to be looking at an area about 2,200 square degrees of the sky, which is about the size of, I think it's about the size of the Orion constellation, that size effectively in the sky. And it's quite special because of the number of CCDs which we have, which are the charge coupled devices which are there for taking the imagery. So there's about 104 CCDs, so there's 4 CCDs per camera. There's 26 cameras. And each camera therefore is 80 megapixels. And so when you think about our phones, which is about, even the iPhone is about 12 megapixels, this camera system which we're building will in fact have 2.1 gigapixels. This is the camera which we're building to launch in 2026. And we look at the sky, and we look at the sky for 2 years, the same region, and we're looking at about 250,000 stars at the same time. And all the stars will be like our sun. And we're looking to see, can you see the transits of the planets passing twice during this period. So basically, if you want to find the Earth, recognizing that you've now found after 2 years, you found a few hundred maybe, okay, then you want to follow up with spectroscopy, and spectroscopy being that you want to look at the atmosphere and you find the water in it, because you've found some planets which are passing in front, they're in the right location around the Sun-like star, and now you're looking at to see whether there's water in the atmosphere. And so effectively it's clear that after about 3 to 4 years after launch, you'll have characterized the atmosphere as well. So we can expect then to have an Earth2 confirmation, the actual, and I think we're going to find many of them, planets like the one we live in, by about 2030 to 2032 approximately. So we found it, okay? So we found Earth2. And the question is, well, if we found it, well, how are we going to get there? Okay, especially, I mean, in the case that our planet's going to be exploding by the time the red giant actually burns up our planet. We have time, of course. But what I want to do with this part of the talk is just explain a bit about the existing rockets that are out there. And the strange thing about this part of the talk is that it looks like science fiction, and yet it's quite factual, because a lot of this is based on what's happening already day to day, and I'll explain why. So let's just start with the height of the rocket, to get an idea of how big rockets are, and then we discuss a bit about their weight. So the height of a rocket, normally, this is the Ariane 5 from the European Space Agency. It's already working since about 1996 or so, 1998. It's 50 meters in height, and 50 meters is it's very difficult to measure. But to get an idea of height, that's myself standing beside one. Okay. And then there's the height of the 60 meter, which was the Ariane 4, which is no longer in existence. So we're building now another one, which is called the Ariane 6, which will be more or less a similar height. And a 60 meter rocket this here is the structure here, which is where they build the rocket upright. They effectively place it here and build up all the components, build it vertically, and then this part here moves out the rocket out to here where it launches. So once you're looking at this area here is in fact this part here. So for 60 meter rocket, well, that's myself here. Then, okay, we're talking about rockets which are going to be much, much higher. Because the bigger the rocket, why is height important? Well, height is important primarily because the higher it is, the longer it is, the more actual mass of propellant, of fuel you can actually.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
notice that are there, the sparklers which are there just to ignite the gas. But watch how the flames actually go around the rocket before it takes off.
Rohde ignition.
10, 9, 8.
That's the igniters there, yeah.
6.
That's just
5, 4, 3, 2, 1. And liftoff. At dawn. The dawn of Orion and a new era of American space exploration.
Now these are these are liquid boosters. So all three of them. Okay, I'm going to stop there because you can watch this one. This one I want to leave a bit to the end because this is the future of space, of rocketry. Okay, a launch of an Ariane 5 rocket costs about 500 million euro. But then the satellites you're putting on top can be like the one launched this morning. The solar orbiter was about 1.2 billion. So you're putting a 1.2 billion satellite on top of a 500 million euro rocket. It costs so much, okay, and it's a once-off. It goes up. It's got the main stage. When the main stage has used all its fuel, it just falls off, comes down, lands in the sea, and it cannot be reused. The upper stage keeps on going to space, and it runs out, and then it stays in orbit, and that's why. Never mind the Starlink satellites which are up there, which we know is going to be thousands in the future, a serious problem. But a lot of the satellites which you actually see crossing the sky, it primarily are the remains of rockets that have been left up there to put the satellites in space. This is the old times. But now what's happening with a lot of rockets is that they put the satellite in space, and then they actually turn around and they enter themselves, so they burn up. So rather than leaving the stages up in space, they actually burn them and get rid of them to avoid that you create another satellite. This one is the future, in my opinion. It's reuse. It's where they, rather than just discarding everything, they can bring down the cost of getting to space because they can reuse parts of the rocket. And for SpaceX, which is based in California, SpaceX are trying to, well, not even trying to, they are, yes. Yeah. This is the first stage, okay? The first stage is, it arrives to a certain point, uses all the fuel, and then it separates, and the second stage continues and brings the satellite on top, because the satellite's inside this what's called a fairing, which is just a protective case to allow it to go through the atmosphere, because the atmosphere, you're going so fast, will burn up any satellite. So you protect the satellite during its ride to the orbit. At a certain point, even the fairing separates. So SpaceX tries to reuse this by bringing it back and lands it on a barge in the middle of the ocean. It brings it back into harbour, fills it full of fuel again, and off it goes one more time. And it's already being reused 3 times, and they imagine they can reuse it up to 10 times. The fairings, they're reusing it by actually, they've got ships which are floating in the ocean there, and they've got big nets. And when the fairing arrives, they try to grab the fairing so they can reuse that. So they're trying to reuse it, and the reality with this is, by being able to reuse, then a rocket like this can cost about 50 million, because you're able to reuse everything. And that's the future, because the more you can bring on the cost of the rocket, the cheaper it is to get to space.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
This is the booster coming back down.
R1 engines on the first stage light, and we have got shutdown before the boost back burn. So currently we're coming up on T plus 7 minutes. The second stage continues to head into orbit. First stage is coming back to the ground ship. Let's go down to the floor to the winding burn and the entry into orbit of the second stage. So as you just saw, the re-entry burn for the first stage is just completed and looks successful. You can still see camera footage from the first stage descending down. Hopefully we'll be able to maintain video all
Okay, so that was one of the early ones. That's why they're shouting so much, because it was really a technology leap to be able to reuse rockets. The first time they did it, it missed. It actually landed on the edge of the barge and fell over into the sea. The second time it landed in the middle, but then kept moving and fell off the edge. So they lost a few rockets in doing it, but then finally they can now have just reusing every rocket that they actually put to space. Okay, so now you can get into space, and you're saving money, you're reducing the cost, so you can actually get to space cheaper. But if you want to go to the moon and Mars, and don't forget our final destination is actually to go to other stars, so what you want to do is you get bigger rockets. I'm going to try and explain why the bigger rockets are there. The key is the weight and the speed, but going to the moon and Mars with people is the next stage. We want to see can we actually go just to our local planets before we worry about going to the stars. And these are the rockets that are in plan. This is the Saturn V, which was actually built there in the 60s or so for going to the moon. And now we have a number of other rockets which are being planned. This here, Falcon Dragon 2, is the one you've just seen that effectively has just come back and is being reused. Then you have another one called the Space Launch System, which is being built by NASA at the very moment, the SLS, which is, it's 118 meters or so in height. So we've been talking about, you've seen the rocket where I was standing, which is about 50 meters. This is more than double the height. And then you got the Falcon Heavy, which is currently is now launching and is working on a regular basis. They used this last year to put a Ferrari in space. There's a Ferrari which is on its way to Mars by the owner of SpaceX. I could think of better ways to use Ferraris, but okay, I'll go with it. And then you have this BFR, big F. Still, I was wondering what the F for a while, but it's Big Falcon rocket, okay? But it's a big Falcon rocket, and then we have the Falcon Dragon. So let's have a look at these other two, the SpaceX, the Space Launch System. Let's see what's the situation with that. Now it's 128 meters high. It can bring 26 tons to the moon. So it's got a serious power to actually to escape the atmosphere and send it to the moon. And let's look at the video. This is just an animation. It's amazing what you can do with an animation, hopefully, if it starts. There you go. So this is what's supposed to happen. ESA. It's the water, there's the sparklers, and off it goes. Okay, stop it there. This, in fact, when I say it's not science fiction, this is the situation as of only a few days ago. The bottom stage is now ready. This is being put upright, and it's expected to launch this year. This rocket, which is 128 meters in height, they will launch it initially without astronauts, and they're going to send it to this module. They're going to put it on. They're going to send it around the moon and bring it back again, just to confirm that first of all the rocket works. And secondly, that it's actually that whatever you put in the rocket will actually survive going around the moon and come back and actually re-enter the atmosphere. Then you have the big Falcon rocket, big FR, which is here, 118 meters high. The idea being to bring to the moon 100 tons more or less, which is a huge weight, and you can even bring. The idea is to bring 110 passengers to Mars. And how on earth would they do this? Well, I'll talk about that in a second. So how we go to Mars. This is a video that's been released by SpaceX, an animation of how they will get to Mars with this rocket. It's I'll leave it to go to the end. It's a very cool video, and then we'll see where they are with respect to achieving their goal. What I want to bring to your attention is the reuse idea. Okay, so look at the technologies being used here and ask yourself, well, how far are we with what they're doing at the present moment with their rockets, with this idea? This part here on top is called Starship. Okay. It's a separate rocket, effectively. So you bring all the passengers up to space, but then if you want to bring them to Mars, they need fuel. So they launch the second part, it joins with the first part, fills up the first spaceship with fuel, and then goes back. It takes about 6 months to get to Mars, depending, well, that's every 2 years, more or less. Otherwise it takes longer. Okay, we'll stop there. Let's start talking about terraforming and stuff like that. But okay, why do I show you this? I mean, how it looks like science fiction. And this is in fact the Starship prototype, which is actually built last year, and it exists. It's being built. It has. They were doing testing with it at I think it was the end of last year, and it exploded. They were doing a pressure test. They were filling it full of fuel, and it exploded on the launch pad. So they built another one, and they built another one, and they actually, on purpose, exploded it only 2 weeks ago. On purpose, because they have to check that if you put astronauts on the top of this, it has to be able to deal with certain internal pressures. And so what they do is they fill it full of fuel and then they over-pressurize it just to see that it actually reaches the quality standards. And so they blew it up again. But the idea here is to use similar motors as being used on the Falcon, on the Falcon rocket, and to launch this in the next few years. And this is what goes on top of the big Falcon rocket. So effectively, we're not so far away from achieving the possibility of being able to send people initially to the moon. There's a Japanese person who's a billionaire who is already signed up to actually go on this to the moon and back. And he's hoping to do this before 2025. So if they go to the moon, can they go to Mars? Okay. Here, okay, I'm thinking 10 years before it happens, but the technologies are already quite advanced to achieve it. Okay, so now we've seen all the big rockets. I want to talk a bit about speed, okay, because you want to go to a closest star, or even a star which has an Earth that we found before and around it. So let's have a look at speed. So speed to get to Dublin, maybe it was a bit faster today actually, but anyway, 60 kilometers an hour is, 60 kilometers, 100 kilometers per hour is what I wanted to go. Very slow. It was raining. Okay. Speed of sound is about 1,235 kilometers an hour. So at this point, let's do it. It's 0.33 kilometers a second. Let's talk about speed in seconds. A rocket, when it takes off, just to put you into space, the velocity which is traveling, at the end of which it separates the satellites, normally is about 8 kilometers per second. If you want to keep a satellite in space, you're normally traveling about 8 kilometers per second. That's how fast it goes. If you want to escape, and you want to escape the atmosphere of the Earth, you want to go to the moon or even beyond, to other planets, you actually have to travel 11.2 kilometers per second. This is why you need bigger rockets. Because if you want to travel to the moon or beyond, then you need to have to travel food. Well, bring food, bring everything that you need that you can actually survive and enjoy your trip for a number of months. In this case, to Mars, it could be 6 months there and 6 months back. So you need to bring it all. So you need a lot of mass, and this is where you need big rockets to send you at this speed to leave. To catch a comet like Rosetta. And here I'll talk just briefly about how we actually speed up satellites in space. So if the rockets that we're talking about maybe can, depending on the weight, because you're trying to send a lot of weight to space, they're huge rockets. They can send tons and tons to the moon. But the reality is, it's if you really want to get faster in space, well, you need to use other techniques. These rockets will release things maybe at 12 kilometers per second, maybe 12.5 maximum. That's what they can use. That's how fast a rocket can release you in space, even the big ones. So if you want to get faster, you need to look for other techniques in space. And this is how we did it for Rosetta. And what you do, it's just effectively increasing the satellite space by using planetary flybys. So you line up the satellite as it's flying through space with the rotation of the planet. And as the planet is rotating, you have the satellite coming in just with the rotation, and effectively the planet itself gives an extra push to the satellite. If you want to slow it down, you come the other direction. For example, we're flying to Mercury with a satellite called Beca Colombo. It's going too fast. We need to slow it down to actually go into orbit around Mercury. So we fly the direction and we try to slow it down, but we also use the planets to slow it down. And so this is how we managed to speed up Rosetta from 11 kilometers per second to 14. And then to leave the solar system, okay, 40 kilometers per second. Why do I mention this? It's because the Voyager satellites, which were launched in the 1970s, now I think Voyager 1 or Voyager 2, one of them, left the solar system more or less. They stopped feeling, let's say, the pull of the sun in about 2012. And they're on their way out, going towards interstellar space, and their speed at the moment is about 40 kilometers per second. So that's currently the fastest object that humans have actually been able to send, and that we can actually achieve in space at this very moment. So how fast is 40 kilometers per second? The speed of light is 300,000 kilometers per second. Closest star is about 4 light years. the time it takes for one light year, the time it takes for the speed of light for it to travel in 1 year. So we've got 40 trillion kilometers to make. So how on earth are we going to increase the speed from our current baseline of 40 kilometers per second to try to go to even our closest star, which is going to require you to travel 300,000 kilometers per second for 4 years in order to get there. Okay. And that's assuming it's Alpha Centauri. Alpha Centauri is our closest, or Proxima Centauri is our closest star. It's a red dwarf. So again, it's not one which we want to go to because it's the one which has major radiation. So we're going to be looking for, if we do find an Earth around another star, maybe 10 light years away, whatever, but it's still very, very far, and you need to travel major distance to get there. So I want to talk a bit about the techniques or the ideas that are being thought about how you actually can speed up. Some thoughts on future ways to speed up satellites in space. And there's one called the Starship project, which is a curious one. The idea is being that they release these very tiny, about centimeter-sized satellites, which have solar cells on them, effectively solar sails they're called, and you hit it with a laser, and the laser from the ground is giving it an extra push, and you can actually send it, they say, at nearly light speed, just from with this what's called Starshot, with these lasers. The problem with this, just some minor little problems I would flag, that you need 1 million or more lasers interlinked to allow you to push it. Okay, the combined power to do this would be something in the range of 100 gigawatts, which is the output of around 100 nuclear power plants together. You only need it for a short burst, but that's still 100 nuclear power plants. And but even with 1/10,000, it's clear. I mean, with the amount of laser energy, you would just explode anything in space, just to turn it to ash. So this idea effectively is a goner just from the very beginning. It was put out there saying, well, this is how you can do it, this is how we can do it, but the money involved in trying to generate this is huge. And it's illogical anyway, because you can never communicate with these things. Because if you want to, when we send a satellite to Jupiter, or even to like Rosetta, it had a 2-meter antenna just to be able to communicate and send back data at about 1 kilobits per second, more or less. It was about 7 kilobits per second. That's kilobits, and that's with a big dish. And the Earth's trying to send something to another star. The only thing you can do is send it, but you can't actually know when it arrives there because you've maybe you destroyed it, but even still, it doesn't have any antenna to communicate. There's another way to do it, which is through solar sails, which is flight by light. Effectively, you build something which is it's like a what's this metal film that you have in what's it called? She's like no, Milo. Well, no, I know it's Milo, but it's sorry.
Aluminium.
Yeah, it's a bit like aluminium, but it's a bit more. Okay, I was just saying it's like what you have in the kitchen when you want to surround something with this metal. Well, it's huh? No, yeah. Tinfoil, yeah. It's a bit like tinfoil, but it's a lot more expensive, okay? But the idea is that you put this object in space and you can deploy it. And I'll show you how it actually works. This is something which is really existing at the moment. It's called the Light Sail project. This shows you sort of expand. They can launch a very small satellite, and it gradually expands. And this is the size of a boxing ring. And with this, just by the sun, the photons coming from the sun, it can actually get to significant speeds. And so the idea of light sails is one way maybe that you can actually get to a certain speed in space. Is it science fiction? Well, the answer is no. I mean, this is it actually working in space when it was launched last year. Okay. But then there's the question, okay, so that maybe can give you a bit faster, maybe you can go to 50 kilometers per second. But the answer is, well, you need to ask yourself, do we really need to travel at the speed of light? Do we have to? I mean, the actual answer is no, you don't. You can just travel at a percentage of the speed of light. You don't have to travel at the speed of light. But if you travel at 1/10 the speed of light, then you'll, instead of arriving at 4.4 light years, maybe 4.4 years, you'll arrive in 44 years. Okay, that's still a long time, but maybe in Star Trek terms it's okay. Okay, but you have to take into account other things. I mean, you have to survive the trip, and there's other things which you should be aware when it comes to the human body traveling in space. Never mind the radiation, the fact that you need major radiation protection on the satellite, but you can put ourselves in cryogenic suspension. Right? So that's one idea. You just freeze down the body and then it wakes up after a period of time. The problem is that in our own bodies, we have in our cells, there's a certain amount of radiation which is gradually just leaking, and over time our cells itself, we cannot survive hundreds of years or even beyond our major life cycle because our cells are slowly deteriorating from radiation gradually being leaked. I'm not an expert in this, but this is a radioactive process that happens with the human body. You also have the point that if you want to go that fast, okay, the G's, the amount of pressure on the body is quite extreme, so it has to be a gradual speed increase to achieve that. So this is just the problems with traveling. If you want to travel at the speed of light, or even partially the speed of light, is whether your body can actually take it, which is extreme. Then there's the ones which you see, the hypothetical ones like warp drive. I have nothing to say about this. I mean, apparently there's lots of people thinking about it, but I'm not convinced about it. But it's good. It's great science fiction stuff, in my opinion. And then there's the only other idea I came up with. So I was thinking myself, well, how on earth, and this is the last slide, how on earth would we actually, if we can't get there, okay, because of the amount of distance that's there, is there another way we can actually get to another star? And I concluded that maybe this is the best way, because we all live it on a daily basis. If you have children, and the fact they go to the disco and they ring you and they say, well, you know, say, listen, can you come collect me? I don't have any transport. Okay? And that's my opinion on how we may be able to go to another star. We'll send a message and let's see if they come and collect us. And Earth2, conclusions, well, I think we will certainly find it in the next 10 to 15 years. But I think it's one giant step for mankind needed to really get there. Thank you. Questions?
That was an excellent talk. We have 3 opportunities to ask questions. One from the floor. From the crowd that are on the floor here. Then you can come and ask him in private, and then you can come and ask him in the Lombardian.
Okay.
So we'll take a few from the floor first of all. You want to field them, Larry?
Go ahead.
Are we only looking for exoplanets around main sequence stars, or are we looking at other objects like white dwarfs or black holes?
I mean, I think black holes is quite extreme, because I mean it's the answer is what they are looking for. How do I give an answer to this? The answer is no. We're not looking for anything else except the main sequence stars, because it's the closest thing that we have at the moment to our own. At least our own sun is passing through this one part of these different types of stars. Black holes is quite extreme because the light is being captured, and they're really you've seen with the gravitational waves that effectively 2 black holes merging. It's quite extreme, and the radiation from that, whether it's gamma ray, I think it's occurring in X-ray, it's quite extreme anyway. What they are looking for, besides the planets, are exocomets, and they have found some comets around other stars, which is around planets, around the stars, but with mixed up with the planets. This is the only other thing we've seen. But yeah, it's primarily the main sequence. It's the type of stars, with the K stars and G stars, etc. that we have.
Would there be any apart from what it would be considered very significant, like if the community is talking about something that would be considered synonymous with life, it picked up by expecting that?
I mean, wasn't there this thing about methane found in the atmosphere of Mars, or at least was measured by Curiosity rover, where they were saying we measure methane, and methane is an outproduct from organic material, and then we found in the end that the European Space Agency has a satellite going around Mars, and when the Curiosity rover was measuring methane, we didn't see anything, and yet we had the most precise spectrometer to actually measure methane. There's certainly other gases produced by mankind, or by the organics that exist in our planet, which you can use as an identifier. But in the end, it's if you imagine that we're trying to compare like with like, you're saying there where you're looking for plants which are producing this, but the plants that we know are the ones which are living on water. There's a water cycle involved in this, and so in the end, the best way, and probably the optimal way, is to look for water in the atmosphere. But there are other, as you mentioned, there's other gases which will help give you an idea which, let's say you find water in the atmosphere, but there are other gases which might actually tell you that there's something to be done with that water. That's an interesting perspective as well, which I don't have anything more than that to say. Okay.
For me, just a simple question. What exactly are solar sails made from? I know they're like tinfoil.
It is mylar. It's mylar. I think you mentioned it yourself.
Nice point.
Yeah. I thought. Well, I think it's yeah.
We need a lecture on light sails.
I think we do.
The planetary society.
Mylar is what we use, in fact, also for the thermal insulation around satellites. It's called multiple layer insulation. It's a very, very thin layers of aluminium, but also this very, very thin metal, which is there for trapping the heat, to keep in the heat around the satellites, and it's very, very light. But
in reality, if you look at the number of people living on the Earth and the actual problems that are encountered in getting to the next nearest 4 light years away, in reality, the probability of getting people off the Earth equals 5 million times in that number of volumes. So it's not basically there'll be a limited amount of people who might get there who will continue what we have as a species, because you know, look at the numbers, it would seem impractical.
Yeah, it is impractical. But then it's not everybody can deal with spaceflight. Just the strength needed in the body to be able to deal with spaceflight is is a lot. And then the cost of launches themselves, as we've seen, it is coming down. But then you want to put, we saw 110 passengers just to be able to get to Mars. I think space tourism is a big deal. It'll happen, but I think we're still missing this one major step to try to get to it. Realism, totally right. It's at this present moment, it's unrealistic. Yeah.
Are nuclear power structures feasible for space travel?
Sorry, say that again?
Are nuclear power feasible?
Well, I mean, Voyager, for example, is the satellites launched in the 1970s are using nuclear power. It's little reactors which are there. So because it's so far away, there's no way they can get the photons from the sun with the solar panels, so they need to use some other heat source or some other source, and that's nuclear power. Nuclear power is certainly an option to, and is going to be needed if you're going to go that far. There's no doubt. The problem is that if you want to launch a rocket, launch a satellite with which has some sort of nuclear reactor on board, you have a huge amount of environmentalists marching around complaining against it, because if there's an explosion, then they're very concerned that you might have a nuclear explosion. Now, is that feasible? The answer is most likely no, because they put it in a container, etc., but one never knows. And so the idea of launching something which has got a huge nuclear source to power so many people to be able to travel to it's a fair point. It's very difficult to do. Sorry? Antimatter. What about it? Well, I mean, antimatter is absolutely. I'm no expert in antimatter, but far from it.
I had a talk about antimatter before, and the problem with antimatter is it currently costs the GDP of the world per gram.
Yeah, that's but maybe if they have a major change or something, some discovery we're talking about, the giant step.
Once you discover the find these how long do you think your estimation before it can be feasible, say, to image say the surface of that actually resulting into like photos of the surface of the moon or something like that, you can actually begin to assess whether it's habitation or.
So how long will it take? If we discover one, then can we actually image the surface? There's a question. I think it's impossible. I think it's impossible. All we can do is you use the light from the star to give you information. Because of this absorption, as I mentioned, the planet's atmosphere will absorb certain frequencies and it gives you information. But to be able to, you saw the imaging technique where you actually see pinpoints of light. But if I was to put my question back to you, which is, well, how much can you image of the surface of Neptune, or even of Mars from the Earth? It's with our major photometric, let's say, instruments that we have, it's still very, very difficult to see, because the atmosphere itself, depending on the atmosphere, it might be opaque, but even if it allows something through, you're always going to be blinded by the star, which is there. So in terms of technology, impossible. Who knows? I mean, and maybe in 100 years' time, it'll be possible. Everything's possible in 100 years' time, isn't it?
Can we take one last question from the floor? Maybe the young chap at the very back.
Sorry. Okay. Go ahead.
There's plenty of time to ask questions in person, so don't worry too much about it.
Is there any possibility of terraforming planets to see their life?
So, any possibility of terraforming planets?
An easy question to end with.
Well, I think it's a fantastic question. It is an excellent question. I mean, when you look at what they're trying, I think it was in Japan recently. I mean, they wanted to get it to rain more. Okay, and so what they do is they pump salt up into the atmosphere, and it actually starts raining. And this is in some ways taking advantage of the fact that there's clouds there, and you actually get a chemical reaction and produce rain. And maybe this is one thing. I think that the terraforming, the idea that maybe that you saw at the end of the video from the SpaceX, is science fiction at the present moment, because in order to do that you need a huge amount of equipment brought over in order to be able to start processing the atmosphere, in order to be able to change what you have there. And it costs so much just to send one person into space. If you want to send this huge engineering structures just to be able to do that, or build them there with 3D printing, it's a lot of work. But I think it's good to dream, and one never knows where we go with this. So I think it's a good question.
Well, we might leave the formal questions from the floor there, but that said, there'll be plenty of time to ask Larry a question. I'm saving all mine for crossing the Lombard in. I have lots of questions to ask Larry then. But he's been very kind to come from Spain to tell us all about the Plato Mission. He's the senior engineer on the Plato. I think it's €1 billion mission in total.
700 million, it's not...
So we want to wish him and the team the very best of success for launch and ultimately for 2030. Anna, our manager, might just hold the front page of the magazine for 2030.
Please do, yeah. In January.
So thank you very much.
Thank you very much.
I'll take the mic down there.
Yes.